In this video, we're going to discuss rational functions and inequalities, and we'll start with rational functions. Rational functions are basically functions of the form or that can be written as the quotient of basically two or division of two polynomial functions, right? And so I have f of x over g of x. So I'm calling my rational function r of x, and it can be written as the division of two polynomial functions. We have the extra specification that g of x cannot equal zero, right? The zero polynomial. And one of the reasons why we don't want g of x to equal zero is because we would be divided by zero, which is called undefined, right? It causes our function to be undefined. Now, sometimes we have actual points that make the denominator zero. And as we've already discussed when we were talking about functions in general, any input value that makes that creates a division by zero causes our function to be undefined. And so we have to find those values in order to find the domain of rational functions. And so the domain may be restricted because of the possibility of divided by zero, which is, of course, considered undefined mathematically. And so to find the domain of rational functions, we exclude the values that make the denominator zero. So for instance, I have this polynomial divided by that polynomial here. So x plus 2 is a polynomial, and I divided by the polynomial x squared minus 4, and together they make a rational function. And here I wanted to find the domain of this function, f of x equals x plus 2 over x squared minus 1. When I'm finding the domain, all I'm worried about is excluding the values that make my denominator zero. Instead of saying that they equal zero, I'm going to say that they are not equal to zero, and I'm going to solve this equation for x. There are multiple ways we can solve this. This is the quadratic equation. We can solve this by factoring. You don't have to solve this by factoring. You can solve by extracting square roots, where you add 4 to both sides and you set both sides. And then you take the square root of both sides and you have these two solutions here. Or you can solve by factoring, which is what I'm doing here. And I get that x cannot equal negative 2 and x cannot equal a positive 2. So my domain is going to be from negative infinity to negative 2, union negative 2 to 2, union to infinity. And this is equivalent to saying all real numbers except 2 and negative 2. And I'm just going to say plus or minus 2. All right. So we're basically talking about the whole real number line, but we're skipping over negative 2 and positive 2. Now, some very interesting things may happen when our graph at those points that are not in our domain. And we've never really focused on this before. The reason why we didn't focus on this when we were talking about polynomial functions is because polynomial functions have a domain of all real numbers. Well, for some other functions, like our rational function, which we're talking about in this section, our domain is no longer all real numbers. And so notice here, if we were to plug in negative 2 or positive 2 into our function, our numerator will be okay, but our denominator will be 0. And so what we want to do is we want to figure out what exactly happens when our denominator is 0. And so I am going to graph this function on our calculator. And so here I have my graphing calculator. I'm going to turn it on, and I already actually have my function plotted here. I know we're not a calculator using class, but what I'm going to do is I'm going to graph this function. And this is what the graph looks like. Notice x equals negative 2 is over here, right? And x equals positive 2 is over here. Now, if I try to trace this function, for instance, if I plugged in 2 into my function and press enter, it should tell me my output value. But remember, 2 is not in our domain. And so what's happening here, notice I plug in 2 into my calculator and my output is there is none. That means my function is undefined there. If I plug in negative 2 into my function, I also see that my calculator doesn't give me a solution there. Now, if I plug in a number that is in the domain, for instance, something like 0, if I plug in 0, press enter, I get negative 0.5, right? But if I plug in negative 2 or positive 2, my function is undefined. There are two things that may happen where at places where my denominator equals 0, right? And so one thing is that, oh, my graph is just going to skip over it. or there's going to be what we call a hole in the graph, or we're going to have a line that our function, a vertical line that our function approaches on either side of positive 2, or that number that makes the denominator 0, but it will never touch that, because if it did touch that line where that line is a vertical line x equals 2, then I will have an output value there, right? So we may have a hole in our graph, or we may have some line that our function approaches but may never touch, all right? Before we talk about what exactly happens and how do we determine whether it's going to be a hole or a line that our graph approaches, what we're going to do is we're going to talk about some important symbols that we're going to use throughout this section. We've already seen some of these symbols. For instance, these bottom two symbols here, this is as x approaches infinity, and as x approaches infinity. And this one here is as x approaches negative infinity, right? But we haven't seen these two symbols here. And these are, and remember, these bottom two here, these were related to the end behavior of our function. And so when we have x approaches a and with that negative sign there, and that x approaches a with that positive sign as a superscript, this is a is always going to be a distinct number. So it's not going to be infinity or negative infinity, but it will be some number like 5 or negative 3 or 7 or some finite number, right? Then what this means is as x approaches a, and we're going to give the extra specification that negative sign is from the left of a. And when you have that plus sign, it's going to be from the, as x approaches a, from the right of a, right? And so basically these things right here gives the behavior of our function as x is approaching that x value. So from either the left or the right. So that minus sign from the left for negative and from the right for positive, because negative numbers are on the left side of your number line and positive numbers are on the right side of your number line. And so I have a graph here. And my graph is one of our parent functions. And the actual parent function that we have here is f of x equals 1 over x, right? That is our parent function. So this graph here is f of x equals 1 over x. This is the graph here. This is the graph here. Now, we already know our end behavior. We can tell the end behavior of our function, but what I want to do is I want to focus in on what's happening here. If I look at f of x equals 1 over x, that domain is basically going to be that x cannot equal 0, right? Because we set our denominator not equal to 0, and our domain is going to be all real numbers except that value. And so it's going to be from negative infinity to 0, union 0 to infinity. And so what happens at that 0, right? Well, we can tell what happens by looking at the behavior of the function as x approaches 0. This is as x approaches 0 from the left. I want to know what my functional values are doing, right? Well, it was approaching 0 from the left. Well, 0's here. The left side of 0 involves negative numbers. And so I'm going to trace what my function is doing. My function is going down indefinitely, right? That means that my function is going down indefinitely as I approach 0. Notice it's going to approach 0 but never touch it because it can't touch it because 0 is not in our domain, right? And so it's going to be, since it's going down indefinitely, I'm going to say negative infinity. And as x approaches 0 from the right, well, 0 from the right, that's numbers close to 0, but on the right side of 0, I'm going to trace what my function is doing, and my function is going upward continuously, right? And so since my function is going upward continuously, I know that that means, or indefinitely, that means positive infinity. When this happens, right, if I ever approach a number from the left or the right, it can be either or, then the line, the vertical line, x equals that number that I'm approaching, is what we call a vertical asymptote. So because I have these two things here happening, then this tells me that the line x equals 0, and it's a whole line, it's a vertical line, so I need to see the x and the equals. It is what we call a vertical asymptote. And so what happens when we try to divide by 0 is our function, as we get closer and closer and closer to 0 from either the left or the right, our function gets larger and larger and larger. Our functional values get larger and larger and larger going up indefinitely to positive infinity, or get larger, the magnitude gets larger and larger and larger and goes to negative infinity sometimes, all right? And so in general, the line x equals a is a vertical asymptote. If our function approaches a positive or negative infinity, all right, I say that the absolute value of the function approaches infinity. This just means f of x approaches infinity, or f of x approaches negative infinity, that looks just like an 8, as x approaches some distinct number, all right? And we'll look at it from the left and the right, and we'll talk about when you get to calculus what this means, okay? And so those are vertical asymptotes. And so notice when we looked at that graph of f of x equals x plus 2 over x squared minus 4, on that graph, we basically had a vertical asymptote. Let's get back to my graph, at x equals 2, all right? We had what we call a hole at x equals negative 2, and I'm going to tell you how to figure out that we have a hole, okay? Our function is, if I factor my numerator, well, my numerator is already factored. But if I factor my denominator, that's the x plus 2 times the x minus 2, right? Notice here, I could cancel out the x plus 2's here. And I'd be left with the rational function 1 over x minus 2. Notice if I set this after I factor and cancel any common factors, and I set this denominator equal to 0 here, and because I don't want my denominator equal to 0, then this is going to give me, that is wrong. This is going to give me x equals 2. So this process here, where I factor and I cancel my common factors, and whatever is left in my denominator, I set that not equal to 0. Those solutions that make that rational expression not equal to 0 are going to give you your vertical asymptotes. For the things that cancel, the x plus 2's cancel. Now, this x plus 2 is still in my denominator of my original rational function. And so it's still that x plus 2 does not equal 0. And I know that you're probably having some issues seeing, oh, nope, you're good to go. And I got x does not equal negative 2. It's at this point where I have a hole in my graph. I have a hole in my graph. So the values that make your denominator 0, both of them are not in your domain, right? So I can look at this to find out where my domain is, right? Set that not equal to 0. If I want to find a vertical asymptote, all right, what I have to do is factor and simplify my rational expression, meaning cancel any common factors. The factors, or whatever denominator I'm left with after I factor and cancel, I set that not equal to 0, and that's going to give me my vertical asymptote. The factors that canceled will create holes in my graph, and that's what happens at that other value that may not be in your domain. To find out the y value of that hole, right? If I wanted to graph the y value of that hole, you just go to your function, your simplified function, and plug in that value, right? So if I want to know the y coordinate of that hole, it's going to be 1 over, I plug my x value where my hole is into this function for x. So I get 1 over, negative 1 over 4. So my hole in my graph is going to be at the point 2, negative 1/4. All right. So we know how to find a vertical asymptote. I've written that down here. Factor and cancel the common factors if possible. And after you cancel those common factors, you set your denominator equal to 0 and you solve for x. All right. To find your holes, all right, we can remove this calculator here. To find your holes, I was about to say something very funny. All right. To find your holes, I'm just going to write this statement. Wholes come from the zeros of the factors that canceled. Okay, so it's the zeros of the factor that cancel. So up above here, oh, I just messed that up. Anyway, wholes come from the zeros that of the factors that cancel. So the x plus 2, that was a factor that canceled, right? And so the zeros of that is negative 2, right? It only has one zero. All right, those are vertical asymptotes. Now let's go to as x approaches negative infinity and positive infinity. We've already discussed this before. That had to do with end behavior, right? So as x approaches negative infinity, remember that's the left side of your graph, right? So this is the same picture of our reciprocal function, 1 over x. We already know that the domain was negative infinity to 0, union 0 to infinity. All right, but when we talk about the end behavior, it's the y values that our graph approaches on the left extreme end of our graph, right? As x approaches negative infinity. So x approaching negative infinity is over here. Notice our function is going to ride this line. It's sort of riding this line here indefinitely. Well, this line here is the line y equals 0. That's our x-axis. The x-axis is the line y equals 0. And so what's happening, I want to know what y value are my y values on my graph getting closer and closer to. And since they're getting closer and closer to my x-axis, and my x-axis is the line y equals 0, then as x approaches negative infinity, f of x approaches 0. All right, now when I think about positive infinity, that's the right side of my graph. As x approaches positive infinity, that's the right side of my graph. My x values get larger and larger. My y values are getting closer and closer and closer to my y-axis once again. And since the y values on my x-axis, it's the line y equals 0. And since my x values are getting closer and closer to my x-axis, and that's the line y equals 0, then I know my functional value f of x is approaching 0. Okay, this is the end behavior. When we have a situation where our end behavior approaches a specific number, then that number is what we call the line that represents that number graphically is considered a horizontal asymptote, right? So the line y equals a is a horizontal asymptote. If f of x approaches a as x approaches infinity, or if f of x approaches a as x approaches negative infinity, right? And so whatever number your functional value approaches at positive and negative infinity would create your horizontal asymptotes. Now to figure out your horizontal asymptotes, I have a polynomial divided by a polynomial. Remember, we use this notation to talk about polynomials divided by polynomials, or polynomials, right? Remember, horizontal asymptotes has to do with x approaches in plus or minus infinity, right? Well, at infinity, only the leading terms are going to be of control here, right? All of these other terms are not going to be as large of numbers compared to your leading term because it's x to the highest power. So what we do to find horizontal asymptotes is we sort of look at the highest exponent, okay? So there's three scenarios. Either the degree of the polynomial on the numerator is going to be greater than the degree on the denominator, or it's going to be less, or it's going to be equal. When the degree on top is higher than the degree on the bottom, right? Some people call that top heavy, all right? Then what happens, an example of this would be something like x to the 10th over x to the 6th. Then as what we can really think of is that 6 is going to cancel with that 10, and we can simplify that to be like x to the 4th. And if I put infinity in for x to the 4th, then what's going to happen is it's just going to be infinity to the 4th power or even more infinity. Or if that was a negative infinity, well, in this case, it's still going to be positive infinity because we're raising it to the 4th power, right? And so for this example here, what we're going to do when we have a top-heavy situation for our rational function, our horizontal asymptote, there is none because our function is going to continue to go up to infinity or down to negative infinity as x approaches positive or negative infinity. So we're going to say there is no horizontal asymptote. And I'm going to start abbreviating asymptotes with the HA for horizontal asymptote, VA for vertical asymptote. When the degree of the numerator, the top, is less than the degree on the denominator, we call that bottom heavy. Or I call it that. Your rational function is bottom heavy. Okay? And so when it's bottom heavy, it's something like, okay, well, let's say if I had x cubed over x to the fifth. Well, once if I can simplify that, I get 1 over x squared. And so that would be like dividing 1 by and we're going to put infinity and negative infinity in there. So let's think about putting infinity in there, or better yet, a million. It's not even close to infinity, but that's close enough. Then that's going to be a really, 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 really small zero. And remember, infinity is just going to keep adding zeros. So I'm going to get a really, 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 really small number, 0.000000000. Okay, you get the picture, right? Which is going or approaching zero, right? And so our horizontal asymptote is the line y equals 0, all right? And then the degree of the numerator is equal to the degree of the denominator. All right, now there's no bottom heavy, top heavy situation going on here. The degrees are exactly the same. That'd be like looking at a polynomial like 3x squared over 4x squared. What happens to those x squareds? They're going to cancel, and we're going to be left with 3/4. There's no way to plug in infinity like we were in the last two examples. We're just going to be left with 3/4. And in fact, that's exactly what happens when we do the horizontal asymptote. All right. The horizontal asymptote is the line y equals, and it's the ratio of your leading coefficients. Now, the way I wrote this polynomial over a polynomial, it had a coefficient of a sub n on the numerator and b sub m on the denominator. So it's a sub n over b sub m. It's the ratio of the coefficients on your leading term. All right. So that's horizontal asymptotes. There are also what we call oblique asymptotes. They only occur in rational functions where there is no horizontal asymptote and the degree of the numerator is 1 degree greater than the degree of the denominator. All right. And so the way we find these is we use long or synthetic division. Remember, you can only use synthetic division if your denominator is like x minus c. All right. So if you don't have that, then you can't use synthetic division. You have to rely on long division. And your actual oblique asymptote, some people call that a slant asymptote because it's going to be a slanted line that your graph approaches. But the line y equals your quotient is what we call the oblique asymptote. All right, we're only going to look at one example here. Let's look at actually, let's look at both of these examples. Nope, I'm going to let you do on your own. Do this one. Do on your own. Let's go to part B and we're going to do this one together. So I'm going to find my vertical asymptotes. Ooh, I think I might have messed up. Nope, I changed it. So I'm going to find my vertical asymptote, right? To find your vertical asymptote, you first factor your numerator and your denominator, right? I'm going to come off and do some scratch work here, right? Because this is a cubic polynomial. And I can factor that by grouping. Out of the first grouping, I can factor out of x squared. I'm going to get an x minus 2. And out of this, I'm going to factor out of 1, and I get an x minus 2. Both of those have a common factor of x minus 2. So I can factor that out, and I get x squared minus 1. All right, which further factors into x minus 2 times x plus 1 times x minus 1, right? And so I have that completely factored. And so my numerator here is going to be x minus 2 times the x plus 1 times an x minus 1. All right, my denominator is a difference of squares. That's x plus 1 times x minus 1. And so if I want to find my vertical asymptote, I have to cancel my common factors, which are those things right there. And so my polynomial really simplifies to a non-rational function, right? All right. But there are no vertical asymptotes because both of my factors in my denominator cancel with my factors in my numerator. And so there is no vertical asymptote, right? Now, if these things wouldn't have canceled in the denominator, what I would do is I would say, oh, x plus 1 does not equal 0, or x minus 1 does not equal to 0, right? But I couldn't do that because they canceled. And so there's holes in the graph instead of having an actual vertical asymptote, okay? There's holes in the graph instead of having a vertical asymptote. Let's go to finding our horizontal asymptote. All right, a horizontal asymptote, we look at whether it's top heavy, bottom heavy, or equally heavy. Since this polynomial is top heavy, there is no horizontal asymptote, right? When it's top heavy, your function goes to infinity and negative infinity and or negative infinity. And so since it's top heavy, we don't have a horizontal asymptote. So this is a kind of weird example, right? We go from having something that's rational. So when we try to find our vertical asymptote, all of our denominators cancel, and so we're left with something that looks like a linear function. It is a linear function, except for the fact that it's going to have holes, right? But there's no vertical asymptote. Not only are there no vertical asymptotes, but since this rational function is top heavy, there is no horizontal asymptote. And so the only other asymptote that we may have is an oblique asymptote. Remember, the oblique asymptotes only occur in polynomials that have that exists such that the degree of the polynomial in the numerator is one more than the degree of the polynomial in the denominator, and that is the case in this example. And so the way that we find this is that we use long division. So I'm going to review our steps to long division, and we'll find our quotient, and then the line y equals our quotient is actually going to be our oblique asymptote. All right, and so x squared goes into x cubed, x times. I go back and multiply that. I get x cubed plus 0x squared minus x. I do my subtraction of each of those terms. Those cancel. I get a negative 2x squared and minus a negative x, which is plus x. With that negative x is 0x. And I get a plus 2 here. And so now I go and I divide this into that. I get a negative 2. Negative 2 times x squared is a negative 2x squared. Negative 2 times 0 is a 0x. Negative 2 times a negative 1 is a positive 2. And I subtract and I get 0. All right, now we could have already known that. We got a remainder of 0. That means that this divided evenly. And we saw that here when we cancel these common factors. And we got x equals 2, all right? And so my oblique asymptote, y equals x minus 2, is the oblique asymptote, all right? So that's how we generally find our oblique asymptote. It's going to be a line, and the actual line is going to be equal y equals your quotient when you do your division, all right? And so now that we know how to find all of our asymptotes, we can use that information as well as information about our intercepts to help us graph these rational functions. Now, when we graph rational functions, I'm going to take an extra step and I'm going to do a table of values. When we were talking about polynomial functions, we didn't take this extra step to get our actual table of values, but I'm definitely going to do it in this example. Let's sketch the graph of f of x equals negative x all over x squared minus 9. I'm going to start by finding all of my asymptotes. So I'm going to start with my vertical asymptote, right? What I want to do is I want to factor everything completely. Notice here that nothing cancels. And so if I'm going to find my vertical asymptote, I set all of my denominators that didn't cancel, which is both of them, both factors. I set them equal to 0 and I solve for x. I get x equals negative 3 and x equals 3. These are lines, folks. And so the line x equals negative 3 and the line x equals 3 would be considered my vertical asymptote. All right. Now I'm going to find my horizontal asymptote. Okay, my horizontal asymptote comes from looking at the degree of my numerator, which is 1, and the degree of my denominator. This is bottom heavy. When your function is bottom heavy, The line y equals 0 is your horizontal asymptote. And so what I'm going to do, remember that asymptotes are features of your graph. They're lines that your functions approach, right? And so I'm going to go ahead and notate my vertical and my horizontal asymptotes on this graph here. I already have them. We usually notate them with a dashed line. And so I'm going to draw a dashed line representing my vertical line x equals -3. X equals a +3. And I had a horizontal asymptote, which is my x-axis. It's the line y equals 0. Remember, your horizontal asymptote actually represents end behavior. So your function is going to end going over here or over here. It may be above the x-axis or it may be below the x-axis, but that's how your function is going to approach your axes. So we have our vertical asymptote, our horizontal asymptote. And remember, oh, I didn't check about the oblique asymptote. Your oblique asymptote, well, if you have a horizontal asymptote, you don't have an oblique asymptote. And you only have an oblique asymptote when it's top heavy, but it's only top heavy by 1 degree. The degree on your numerator is 1 larger than the degree in your denominator, and that's not the case in this example, which we don't have an oblique asymptote. I'm going to find my x and y intercepts if they exist. So let's find our x-intercept, right? To find your x-intercept, you let your functional value or your y be 0. And so I'm going to get 0 equals -x over x squared minus 9. What I can do is multiply both sides or cross multiply, meaning take the x squared minus 9 and multiply it by 0. I'm going to get 0 equals -x. So that means x equals 0. So the point 0, 0 is my x-intercept. So I can go ahead and plot that. Notice this plot is on my graph. It's on my graph, right? By the way, because the only way for a fraction to equal 0 is for the numerator to equal 0. So if I have a single fraction, now if I had more than one fraction over here, this wouldn't work. But since this is a single fraction, your x-intercept is always going to be the 0 of your numerator. The 0 of your denominator is not going to be in your domain, right? Because that'd be divided by 0. Now, this is the origin, so I automatically know that this is also my y-intercept, right? Or you can just plug in 0 for x here and 0 for x there, and you're going to get 0 over -9, with 0 divided by any number besides 0 is 0. And so we see that our y-intercept is also that. Now, I'm going to submit to you that we don't have enough information to graph right now. We know that our graph is going to approach this vertical line. It's going to approach this vertical line. It's going to approach these lines at infinity and negative infinity, but I don't know how to draw my graph. And so I submit that you need to use some tables of values. Now, I'm particular here when I use my table of values because I don't want to do a lot of work, all right? And so with my table of values, I'm going to need some space. And so I'm going to move some things around. Hopefully this won't get confusing. I'm going to slide this over a bit, and I want to do a table of values. And in my table of values, I'm going to put x and my y. And what I'm going to do is I'm going to focus on, because I'm not going to have a calculator, x over x plus 3 times x minus 3. That's the factored form of everything. And what I'm going to put in my table is and I'm leaving some space here. Notice how I'm leaving some space. I'm putting my vertical asymptote values there. We know if we try to plug that into our function, we're going to get a statement that's undefined. But what's going to help me graph is to know how my function approaches these vertical asymptotes, right? So at -3, is it going to approach negative infinity from the left or to the right? Or is it going to approach positive infinity from the left and the right? We need to know that information. And so what I'm going to do, and this is going to seem very weird, I'm going to pick a number close to -3, but smaller than -3, like -3.1, and then a number to the right. So this is on the left of -3, and this is on the right of -3. Think about your number line. You get -3.1, -3, -2.9, so on and so forth. So this -3 is on the left, that -2.9 is on the right. When I go the opposite direction, we get 2.9, 3, 3.1, right? So I'm going to use 2.9. That's my, as x approaches 3 from the left. And then I'm going to use my 3.1 as x approaches 3 from the right. And so basically, when we have these vertical asymptotes, what we're doing is we need to fill out these types of things here as x approaches a from the left and x approaches a from the right, because I need to know how my graph is going to approach this vertical asymptotes. Sometimes it approaches it this way, and at other times it approaches it at different ways, right? So what I'm going to do is I know that these are going to be infinity or negative infinity, but I got to choose which one it's going to be. So all I really need to know is whether when I plug in -3, am I going to get a positive or a negative output? Because if it's positive, I'm going to approach infinity, and if it's negative, I'm going to approach negative infinity. So I'm going to plug in -3.1. Okay, that's the negative sign there. -3.1. -3.1, plug in for x in my numerator, that becomes a positive. -3.1 plus 3 is a negative. -3.1 minus 3 is a negative. A positive divided by a negative times negative is a positive. That's going to be positive. So I'm going to put a positive infinity there. When I plug in -2.9, I get a positive divided by a positive times a negative, which is a negative infinity. Now, -3.1 was to the left, and my function is going to positive infinity. This is the left side of -3, and I put an arrow there to let me know that I'm going to positive infinity. -2.9, I'm going to negative infinity. -2.9 is to the right, and so I'm going to go to negative infinity. So I'm going to put that in my graph. Now I'm going to plug in 2.9, right? So this is my next part. A 2.9, plug it in for x, I get a negative. 2.9 positive times a negative. That's a positive infinity, right? Because negative divided by negative is a positive. So on my graph, 2.9 is on the left side of 3. My function is going to positive infinity. And if I plug in 3.1, which is on the right side, I get a negative divided by a positive times a positive, which is a negative infinity. And so on the right side of 3, my function is going to go to negative infinity, right? So I have all of the information I need. I know that my graph has end behavior to the left. It's going to be continuous at every value except it's got to skip over these vertical asymptotes, right? So if my function has the end over here and it has to go to positive infinity here, then my graph is going to look something like this, right? It's got to skip over this vertical asymptote, but on this side of the vertical asymptote, it's going to go to negative infinity. It has to go through my x and y intercept, and it has to end up here. So my graph is going to do something like this. I'm just going to draw a smooth curve, all right? And then it's got to approach that line and go to positive infinity there, but it's going to approach on this side negatively, and it's got to end with end behavior over there. So my function is probably going to do something like that. Now, I know that this part of my graph is going to stay below my x-axis because there are no other x-intercepts. So I don't want to see my graph go above here. And also, since there are no other x-intercepts, my graph has to stay above my axis here and then ride that line to honor the end behavior. And so this is what the graph of this function looks like. I know it's a lot, but there we go. Okay. And last but not least, we want to be able to solve rational inequalities in one variable, right? And so not only do we want to graph rational functions, but we also want to be able to graph rational inequalities. And so, or solve rational inequalities. So what we have to do, right? We always want to compare things to 0. All right, it's harder to compare things to a different number. So the first thing we're going to do in solving these inequalities is we're going to get everything on one side and 0 on the other. So I have x plus 2 over x minus 3. I add 1 to both sides, so that's plus 1 is greater than or equal to 0, right? What we're going to do on this side right here, where all of my variables and terms are, is we're going to write this as a single inequality, rational expression, write it as a single rational expression. That means I need to get a common denominator. Well, this one has a denominator of 1 because 1 is the same thing as 1 over 1. So my lowest common denominator is x minus 3. Well, this one already has the x minus 3. But I can write that as x minus 3 over x minus 3, and I have that right there. Now I can write this as a single rational expression with this denominator, and I can add the values across the top. I'm going to go ahead and add the x and the x, which makes it 2x, and the 2 plus the negative 3 was a minus 1. So I have this as a single denominator, rational expression. Now we're going to factor the numerator and the denominator. Well, mine are already factored, so I don't have to do that step. And then we're going to find the zeros of the numerator and the denominator and plot them on the number line, right? Now remember, my zeros of the numerator, these are the things that make this actual rational function 0, right? So I set that equal to 0. And since I have an equality here, I'm going to remind myself to use a closed circle when I plot this on the number line. Now, if that were not an equality there, I would use an open circle. But for zeros, which only come from setting your numerator equal to 0, right? That's the only way that you're going to get a real x-intercept. We get x equals 1/2, right? I'm going to use a closed circle there. Elements not in the domain are always going to be open. All right, they're always going to be open because they're not in the domain, and that's going to be coming from setting your denominator equal to 0, right? And so we know that x cannot equal 3, so I'm going to use an open circle for that one, right? And so I'm going to put 1/2 on my number line and 3 on my number line. I'm going to use a closed circle for 1/2. Notice again, when I set my numerator equal to 0, it's going to give me my x-intercept, or where my rational function crosses my x-axis, right? And if I have an equality there, I'm going to use a closed circle. But if I don't have the equality, then I'm going to use an open circle. For the values that make my denominator equal to 0, they're not in your domain. And so you're always going to use an open circle with those because your function, your rational expression can't equal that. And then we use our test point method, right? So for a test point, I'm going to use 0 on this interval. I'm going to use 1 on this interval, and I'm going to use 4 on this interval here. When I plug in 0, plug it into the entire function, I'm going to get a positive here. When I plug in 1, I'm going to get a negative, and when I plug in 4, I'm going to get a positive. Notice there's no multiplicity type thing going on here, I don't believe, and so we're not going to be worried about, well, it may happen actually. I think the multiplicity actually may be a little weird with these, so I'm not going to rely on that. I'm going to use my test point method. Maybe we'll talk more about that in class. All right, but I want this to be greater than or equal to 0, so I'm going to shade in this area here and that area there. And so the solution of this will be from negative infinity to 1/2. I got to use a bracket because that's closed. Union, I've got to use a parentheses because that's open. 3, comma, infinity. All right, and that's how we can solve rational inequalities. This concludes this video. I'll see you during the next one.